A fusion plasma is a fluid that carries its own currents and makes its own magnetic field. The study of how that fluid balances and where it breaks is called magnetohydrodynamics, MHD. It is the difference between a plasma that sits still and one that tears itself apart. Start with balance. A confined plasma wants to expand. The magnetic field pushes back. Where those two forces cancel, the plasma settles onto nested magnetic surfaces like the layers of an onion. The equation that describes those surfaces is the Grad-Shafranov equation. Solve it, and you get the exact shape of every flux surface inside Hyperion. The geometry the rest of the physics lives on. The pressure the field can hold is measured by a number called beta, the ratio of plasma pressure to magnetic pressure. High beta means you're getting a lot of plasma for your magnet. It is a measure of how efficiently the machine works. But you cannot raise beta forever. Push too hard, and the plasma goes unstable. So we track a normalized version, beta N, that folds in the current in the field, and compare it against a hard ceiling. That ceiling is the Troyon limit. For Hyperion, we hold beta N at or below 5.0. It is a line we design under, not a target we chase. Margin is the point. The next guardrail is the safety factor, Q. How tightly the magnetic field lines wind around the torus. At the plasma edge, we keep Q minus 95 at 5 or above. Below that, whole classes of instability wake up. The most violent of those is the kink. If the field lines wind too loosely, the entire plasma column can buckle sideways like a garden hose whipping. Holding Q high is what keeps the kink asleep. Then, there are ballooning modes, where the plasma pressure is steep and the field curves the wrong way. On the outboard side, the plasma can bulge and blister outward. Beta and shaping together set how much pressure the edge can take. A spherical-tokamak has a natural advantage here. Its low aspect ratio lets it run at high beta before these limits bite, so we get more plasma pressure inside the same stability envelope. Vertical stability is its own problem. An elongated, tall plasma is inherently top-heavy. It wants to drift up or down and hit a wall. We hold it in place with fast feedback coils that push back in milliseconds. The shape itself is a design tool. Elongation stretches the plasma tall. Triangularity pinches its cross-section into a D. Together, they set the boundary and, with it, the stability. Hyperion runs at negative triangularity, delta of minus 0.30. The D faces the other way. That single choice suppresses edge-localized modes, the ELMs, that would otherwise fire bursts of heat at the wall. One slower instability remains, the resistive wall mode. It grows on the timescale of the surrounding metal wall, and we hold it with that wall plus active feedback, the same philosophy throughout. Watch the limit. Keep the margin. That is the equilibrium story. Solve for the surfaces, stay under beta N 5.0, keep Q 95 above 5, shape the plasma to kill ELMs, and feedback control what is left. All of it is in open simulation, a conceptual design you can check, not yet an operating machine.